Hello everyone, my name is Yi-Chun Chen. I'm a fourth-year PhD student from UCLA. Today I'm going to present my recent work, Column-Randomized Linear Programs, Performance Guarantees and Applications. This is a joint work with my advisor, Professor Velebro-Misic, and he is from UCLA as well. In this research, we consider solving large-scale linear programs. Specifically, we consider a linear program with a large number of columns and relatively small number of constraints. Such large-scale linear program has various applications in revenue management and pricing, such as network revenue management and nonparametric choice model estimation. Since enumerating all columns is usually infeasible, a typical approach to solve this type of large-scale linear programs is column generation method, which introduces one column at a time and iteratively solve the linear program. This is the detail of the column generation method, and the key step is at step 2, where we find a new column that minimizes the reduced cost. We call step 2 the subproblem, and the subproblem is usually NP hard and has to be solved by integer program. For example, in the cutting stack problem, the subproblem is a knapsack problem, which is NP hard. In vehicle routing problem, the subproblem is a set partition problem, which is also NP hard. In choice-based network revenue management, the subproblem is proved to be NP hard for many choice models. And finally, for nonparametric choice model estimation, the subproblem is also proved to be NP hard. So we have seen that although column generation method is designed to solve large-scale linear program efficiently, it is still computationally hard for the following 2 reasons. First, searching for columns by solving a subproblem is computationally challenging. Secondly, since we sequentially add columns to the optimization problem, the overall procedure prevents us from applying parallel computing technique. Therefore, it is inefficient. So instead of column generation method, let's just try a simple and a naive idea. Let's say we just randomly sample a set of columns. Then we solve the linear program that consists of these sample columns. In this way, we have the advantage that doing sampling is much faster than solving a subproblem. And also we can apply parallel technique to have enough number of columns. This is inspired by the random feature selection technique in machine learning. For example, in image processing or in natural language processing, we may have seen hundreds of thousands of features. And the common approach is to randomly select a set of features and then apply the standard machine learning method. Overall, we call this procedure the column-randomization method. And the question is, can such a naive idea work well? If it works well, can we provide theoretical guarantee to its performance despite that there's a lot of randomness happens in this optimization problem? The answer is yes to both questions, and we will show that in the following slides. Before I propose the method, I first want to make some definitions that will be used throughout the presentation. I call the original large-scale linear program as the complete problem, and I denote it by P and denote its dual problem by D. For any optimization problem, I use F to represent the feasible set, and I use V to represent the optimal objective value. For any optimization problem P1 that shares the same objective as the complete problem, but with smaller feasible set, I define the difference delta as the difference of the optimal objective value of problem P1 and optimal objective value of problem P. We notice that this quantity is always non-negative because problem P1 is with smaller feasible set. We can further interpret this delta as the optimality gap or suboptimality of solving the complete problem P by the optimal solution of problem P1. Since I will use randomness in our optimization method, here I want to give a formal definition. There will be a user-defined procedure that randomly selects a column on the constraint matrix A. That is to say, rho randomly generates an index J from 1 to n, then returns the corresponding column A sub j. We can define Cj as the probability that index J will be chosen by the randomization scheme rho, and use the boldface C to represent the entire distribution. Then this is our proposed column-randomization method. We first sample k indices by a randomization scheme rho. Then we collect the corresponding columns and the corresponding cost coefficients, and then we solve the following optimization problem. I called it the sample problem, PJ. This sample problem involves with the sample columns and the sampled cost coefficients that we obtained before. And then we return the optimal solution of this sample problem. So we noticed that this sample problem can be reformulated in this way. That is, only for components that are chosen by the randomization scheme can be non-zero. Because of this reformulation, we know that the optimal solution of the sample problem can be immediately converted to a feasible solution for the complete problem P. This can be done by just simply enlarge the optimal solution of the sample problem to full size, and then putting 0 to those components that are not chosen by the randomization scheme. The question is, how does this optimal solution of the sample problem perform in the complete problem P? Or I can say, what is the optimality gap for this sample problem with respect to the complete problem P? To answer this question, we propose the following theorem. We let Pj to be the sample problem in algorithm 1, and we use A sub j be the corresponding constraint matrix. Let C be a positive constant. Then we define the following optimization problem. I called it the distributional counterpart, because there's an additional constraint that links to the sampling distribution C. Then with high probability, the following statement holds. If the sample problem is feasible and the constraint matrix is full rank, then the optimality gap of the sample problem is bounded by sum of two terms. The first term is the optimality gap of the distributional counterpart. The second term converges with rate 1 over square root k, k is number of sample columns, times some constants relates to the complete problem P. To the best of our knowledge, this is the first theoretical guarantee on the objective value performance of column or constraint sampling method for generic linear programs. Some related works includes DeFarias and Benroy, Calafiori, Gancampi, and Asfahani et al. However, these works, they either make assumption on the problem structure and the sampling distribution, or they didn't prove the performance in terms of objective value. Instead, they prove feasibility. In contrast, our results here and our proof technique are free from any assumption on the problem structure and any sampling distribution. Our proof utilizes concentration inequality from statistics, and we also use the classic sensitivity analysis for linear programs. So far, we only discussed linear programs in standard form, but the results here and the theorem can be applied to linear programs in canonical form as well. In theorem 1, we state gamma as a constant. We can further obtain its exact value for various applications such as network flow problem, Markov decision process, covering and packing problems. And we further derive problem-specific guarantee. And here's an example. We apply the color randomization method to solve Markov decision process. And we notice that in this bound, we work out the exact value of gamma to represent it as the infinite norm of the cost vector divided by 1 minus theta, where theta is the discount factor. Finally, I want to comment that the theorem and the proof technique here can be applied to portfolio optimization problem as well, which can be with Lipschitz objective, therefore possibly nonlinear and non-convex. So far, I only mentioned rho as a user-designed randomization scheme. And here I want to provide some guidance about how to design such a randomization scheme. If we have some prior knowledge about the problem, such as relative importance of variables, or if we have an outcome of a heuristic method, then we can design the randomization scheme based on that. Otherwise, a nearly uniform randomization scheme rho that covers as many columns as possible can generally work well. And we will show that in the following slides. From computational viewpoint, our method has the strength that we only need to do sampling. We don't have to solve the NP hard subproblems. Therefore, we can save a huge runtime. And the sampling step is very suitable for parallel computing. An obvious weakness of the method is that the shrinkage of optimality gap is slow when number of columns k is large. This is due to the shape of 1 over square root k in the bound. If exact optimality is a concern, then one can combine the proposed method here with the column generation method, but simply treat the result of the column randomization method as a warm start for the column generation method. This implies that our method has the potential to improve existing column generation methods, meanwhile provides strong theoretical guarantees. To numerically test the performance of column randomization method, here we consider the problem of estimating ranking-based choice model from data. We use S to denote an assortment. We use head V to denote the predicted choice probability, and we use V to denote the empirical choice probability from data. To estimate the model, we want to find a distribution lambda over all possible rankings, such that the resulting predicted choice probability is close to the empirical choice probability from data. This is the resulting optimization problem. And we notice that the constraint matrix AS here is a mapping from each ranking to each decision under assortment S. Therefore, in this optimization problem, each column corresponds to a ranking. A crucial fact is that even if there are only 9 products in the market, there are up to 3 million rankings to consider for this estimation problem. That is to say, there are 3 million columns in this optimization problem, and therefore it is infeasible to enumerate all columns. And we notice that this problem is in the form of portfolio optimization problem, and therefore, as we mentioned before, we can apply the column randomization method to solve this problem. We design the randomization scheme as follows. We first sample a ranking, or we can say a permutation of integers from 0 to n, uniformly at random. 0 is the no purchase option, and integers from 1 to n are products in the market. Then we convert the decision of this ranking under assortment S to a column of A sub S. We notice that step 1, sampling a ranking, can be done as a one-line command in most programming languages. Therefore, the sampling step is computationally easy. We use this procedure to estimate the ranking-based model from the synthetic data generated by a multinomial logic model. And this is the result. The first two columns shows the size of the problem. That is the number of products in the data set and number of assortments in the data set. The bigger data set corresponds to a bigger estimation problem. The third column is number of sample columns in the column-randomization method. And the fourth column is the corresponding optimality gap if we solve the sample problem. And the fifth column is the runtime of the column-randomization method, including sampling and solve the sample problem. And the last column is the runtime for column generation method to reach the same optimality gap as the column-randomization method. When the problem is small, that is the case that there are only 6 products and 50 assortments, both column-randomization method and the column generation method terminate within 1 minute and return optimal solution. However, if we enlarge the problem size to the case that there are 10 products and 150 assortments, then column generation method needs almost 3 hours to solve the problem. Meanwhile, the column randomization method only needs 3 seconds. To conclude, in this presentation, we propose the column randomization method. We provide theoretical guarantees to its performance, and we show the effectiveness of the method in choice model estimation. Due to time limit, I skipped some content from our paper. The first result is about the numerical experiment in the cutting start problem. We showed that the column randomization method can save up to 60% of the runtime of the column generation method. In our paper, there's an interesting section about how to sample statistically dependent columns and what is the corresponding performance guarantee. So please check out our paper. It is available online, and here's the link. Thank you for your listening.